after making a lot of careful measurements, we've been able to discover or come up with a relationship between force and the size of the charge of the objects interacting and the distance between them. And this is called Coulomb's law. So Coulomb's force, it is a force just like gravitational force or normal force or frictional force. It's a force, has units of newtons, and we find it's proportional to the product of the size of the charges of the two objects interacting. And it decreases very fast. It decreases the square of the distance between those. So if I were to draw this out, I'd say here's one charge, here's number 1, and here's number 2, and the distance between their centers is r. Okay, so if I double r, make them twice as far away, this force is going to drop by 4 times because it's inversely related to the square of that distance. Whereas if I double the size of charge 2, then I'm just going to double the force because charge 2, it's linear in the size of charge 2. But if I double the size of charge 1 and double the size of charge 2, then the force would go up by 4 times because it's linear to the product of those two. So I get 2 times 2. Okay, so that's the proportionality. Now there's a constant of proportionality that we often write as simply K. Okay, and what's interesting about K is its size. Okay, if you remember back from the gravitational force is written really similarly. I'm going to write Fg, so this is the universal law of gravity. Newton's universal law was in magnitude g, this constant g, times m1 times m2 over r squared. First of all, I just love it in the sense this is charged particles. We're talking atoms or electrons interacting with other electrons or other charged particles. This is planets. It's everything with mass, but we generally see this with planets, with the moon, with the sun, with galaxies. The relationship is uncannily the same form. It's just crazy. This one is proportional to the product of the masses, and it gets smaller as the square of the distance. This one's just simply proportional to the product of the charges, and it also decreases as the square of the distance. It's just an interesting similarity between them. Now what's important is how big is g? Okay, the order of g is 10 to the negative 11. Okay, 10 to the negative 11. That is crazy small. So 10 to the negative 11. Super small. That's why we need planets with masses the size of planets to be able to see some significant force. Okay, how big is K? Alright, K is a lot bigger than G. Okay, in fact, K is equal to 8.99 times 10 to the 9th, okay, in its proper units. Alright, so that is huge. That is massive, which means this force ought to be fairly easy to see, and you can. When you can charge a cork ball, hang it on a thread, and then charge a plastic rod with like a Bic pen and rub it with wool, and you can see this effect fairly significantly because that force this constant is so big. It doesn't require very big charges to have an appreciable effect. Okay, and so that's what's important about this constant. It's just how big it is. This is a strong force compared to the force of gravity. Okay, now another thing about it, just like force of gravity, is the force. They're vectors, so these both ought to be vectors. Okay, they also both point along a line between the two objects, pointing from whichever one we say is doing the acting to the one being acted on. So technically, I could, for this one, I could say that this is the force by 1 on 2, so 1 on 2. Okay, I could say that, and so 1 would be the one doing the acting, so my r vector would be pointing in this direction, and point from 1 to 2, because 1 is acting on 2. Alright, now the thing that's important too is these charges could have a sign. One could be positive, one could be negative, or they both could be positive, they both could be negative, but they just have a sign. And so we do know from our experiments that opposites attract and likes repel. And so repulsion would be a positive force. If these were repelling, then the force by 1 on 2 would be that way. And so this should have an overall positive because it should end up in that direction. Now if K is positive, R squared is positive. Okay, and so for that to be true, if these were like charges, okay, then these would have the same sign, and whether they are both negative or both positive, we're going to get an overall positive. So that ends up being a total positive force, or a force in the positive direction. Now we also know that opposite charges attract. So if one of these is positive and one of these is negative, the force ought to be towards them. Okay, so the force on 2 by 1, if they're opposite charges, should be in the negative r hat direction. And so let's just say Q1 is negative and Q2 is positive. Well, then we get an overall minus sign that then does agree with that attraction that we've observed. Now with force of gravity, the masses are always positive and it's always an attractive force, so it had an overall minus sign placed algebraically out there. Whereas this one could be repulsive or attraction, and it comes by having the sign embedded inside the charge.